Today we'll be talking about frequency modulation and how to prove its equation. Before we get into it, just a quick reminder of what modulation is. Modulation is a process of transferring a low frequency signal across a long distance. You know how you can't shout or call your friend, or you can't call home just by shouting when you're in school because of just how far the distance is. So to help with this, engineers found a way to put your voice in a high frequency wave so that it can travel long distances. And high frequency just means very, very fast, right? So frequency modulation is a technique of conveying information by varying the frequency of the carrier wave in accordance to the instantaneous amplitude of the message signal, while the amplitude of the wave is kept constant. It's a method of communication where the information is carried by changing just how fast the carrier wave oscillates. Frequency, as we've been told, is just the number of cycles per unit time. It's, if you can see my screen, well, it's how many of these cycles occur at a certain instant of time. So if we say this is one cycle, sorry, I'm coming. If we say this is one cycle, then this particular time is 2 seconds. My frequency, therefore, is equals to number of cycles, which is 1 all over 2, which would be 0.5 hertz. Now that we've gotten what frequency is out of the way, what actually occurs, what happens? So in frequency modulation, the frequency of the carrier wave is changed or altered according to the instantaneous amplitude of the message signal, while other properties are kept constant. What that means is that the frequency, which is just how number of cycles, would either increase or decrease based on the message signal. So that's why the modulated signal here, kind of, you see, it looks a bit different from the unmodulated RF carrier. Increased. The amplitude of the message signal increased. The frequency of the carrier signal increased as well. And as the amplitude of the message signal decreased, the frequency of the carrier signal also decreased. I have a better diagram here that kind of highlights or really communicates that thought. So this is our normal message signal. This is our carrier signal. After modulation, you can see when the amplitude is high over here, when the amplitude is high, when the amplitude of the message signal is high, or is positive, the modulated signal looks a bit jam-packed. More cycles occurred in this particular time spacing. And more cycles actually means an increase in frequency. And when the message signal was negative, or he had a low amplitude, spacing, it had a lower frequency than the original carrier, meaning there's more space, meaning less cycles occurred in that particular time period. I hope you understand this. So now we're going to go into the derivation of the frequency modulated signal. Let's say our message signal is m of t am cos wmt. Our carrier signal is AC cos WCT. And our frequency modulated signal, which is the final product of modulation, is equals to AC cos theta. First thing you ask is, what is theta IT? Well, coming here, theta IT, which is what's over here, theta IT is just the instantaneous angular displacement or the phase. It just describes the position of a waveform, right? I'll prove that mathematically right now. So let's get into the, well, straight away, we know that we know what WMT and WCT are. Alright, let's have what we know. WMT is simply the angular frequency. The angular displacement, for us to define angular displacement, we have to define angular velocity or angular frequency. Angular frequency is equal to the rate of change of phase. Theta of t is actually the phase of the wave, right? So my angular frequency will be equal to and of course our interest is what our phase is equals to. So our instantaneous phase is equals to the integral of our instantaneous angular frequency. So let's call this equation 1, very key equation, right? Moving on, let's now derive a formula for our instantaneous angular frequency. Our instantaneous angular frequency is equal to the angular frequency of the carrier plus kf m of t, for which is the frequency sensitivity times the message signal. I'll explain why this formula makes sense right now. So let's go back to the graph. So when the amplitude or the instantaneous amplitude of the message signal increased over here, when it was positive, when it was negative, that was when the frequency of the modulated signal increased or decreased. So of course we already know that there's a direct relationship between the amplitude of the carrier. Sorry, there's a direct relationship between the amplitude of the message signal and the amplitude of the modulated signal. And that relationship is this right here, right? So let's go on, let's continue with the math. We're going to substitute this into this equation. We're going to substitute this into this. So our phase is equal to the integral of so now we already know what our message signal is, so we're just going to find the integral of our message signal and then plug it back in this equation. We know that when we integrate cos, we get sine. So if we integrate cos nx, we have sine nx over n, and our n is simply the WMT. Our n is simply the WMT. Should I use a different variable aside from n? I hope you guys understand. So our integral of m of t is equal to, so we're going to plug this back into the equation for phase, instantaneous phase. So our instantaneous phase is equals to WCT plus, okay, oh, mistake, forgot to add. So to make this equation a bit more compact, they included a constant. That constant is called the modulation index. Modulation index is equals to frequency sensitivity multiplied by amplitude of the message signal all over the angular frequency of the message signal. So I'm going to plug that variable in there. So this, we can actually stop here because this is the final equation. But just let's express angular frequency in terms of normal instantaneous frequency or normal frequency. Okay, wait, let's stop here for now. And then let's plug back all of these into the main equation for frequency modulated wave, which is this. So our frequency modulated wave will be equal to the carrier amplitude. You see the amplitude didn't change. Cos, let me use a different color for the brackets over here. All right. So this is the equation for frequency modulated wave.